hydrostatic equation hydrostatic equation。咁呢個 hydrostatic equation 咧就主要係講緊咧一啲嘅靜止嘅流體咧特別係液體啦咁佢嘅一啲嘅 pressure 同埋佢嘅elevation 之間嘅一個轉換靜止嘅流體咧，咁佢總體嚟講咧，佢哋嘅佢嘅 pressure head 加埋個 elevation head 咧係等於一個常數嘅。咁呢個常數咧喺同一個液體入邊咧係相等嘅咁所以咧係通過呢一個咧去估算唔同嘅 location 嘅一個 pressure通常就係咁做嘅如果由上面嘅一個 point 去計算底下嘅，即係below 嘅一個 point 嘅 pressure 咧，就會加佢嘅 ρgh。如果由下面去 estimate 翻上面嘅 point 咧，就減 ρgh。大致上嘅原則咧就係咁啦咁另外就係關於呢個嘅hydrostatic force 呢個水嘅即係液體嘅靜力學act 喺一個 surface 上面嘅時候咧，即係特別係呢一種嘅，即係act 喺單邊嘅個 plane 嘅 surface 嘅時候咧，我哋主要係要記得咧就好簡單嘅道理咧，就係佢嘅 pressure force 咧個計算嘅大小咧，就係會用喺 central 嗰個 point 嘅 pressure 乘翻呢個 surface 嘅 area 就主要係咁樣嘅啫常見嘅都係長方形圓形嗰啲嘅 surface 多啲嘅咁因為 central 呢個 point 嘅 pressure 係代表住一個 average 嘅 pressure， 所以咧就個 force 嘅大小咧就通過咁樣計算嘅。而個 force 咧佢有個 action point 當我哋如果要解決一啲譬如話我哋需要知道某些情況下，好似譬如話一啲嘅咁樣嘅渠蓋一啲嘅渠蓋咁，佢呢邊咧有一個嘅呢邊有個入邊有個水位啦，出邊有個水位啦咁就問幾多嘅水位，呢兩邊水位係幾多時候咧？呢邊會被推開咁樣之類嘅咁如果係要咁嘅話，我哋就需要知道佢哋個 force 嘅一個 action point， 而通過 moment 嘅 equilibrium 咧去推算嘅咁所以咧需要知道嗰個force 嘅 action point 喺邊度咁呢個 action point 咧就係喺一個叫 center of pressure 嘅位嘅咁呢個 center of pressure 咧就要通過呢一條式咧去計算嘅咁呢個YP YC 就係 central 到水面嘅呢個即係水面呢個嘅 intersection 嘅 distance 到 point O 嘅呢個位嘅 distance。咁 YP 亦都係由 center of pressure 到 point O 嘅呢個 distance。就跟住呢度咧 second moment of 呢個 area 係個形狀嘅，咁就會查找翻咧係對應嘅形狀咧去替換翻呢個嘅 second moment 圓形啦橢圓形啦同埋呢個嘅長方形啦橢圓形咧佢呢度咧係個 second moment 咧係 pi AB cubic 除以4嘅咁呢個 AB 咧並不是講緊佢嘅長邊同埋短邊嘅呢個 half width 半長，其實佢就係講緊咧 A 就係講緊 horizontal 嘅 half width，B 就講緊 vertical half width。咁所以如果如果有啲時候遇到個情況係咧個橢形咧係咁樣嘅時候咧，咁呢度計算 second moment 嘅 A 咧就會係呢個嘅呢度就呢個係 A。咁呢個咧就係 B 嘅 ，OK。咁所以因為佢呢個係second moment about 呢個嘅 x axis about x axis， 所以佢嘅呢度嘅 AB 咧就係講同佢呢個擺位咧係有關係嘅，而唔係用個長短去界定嘅係佢嘅擺位去界定嘅。咁呢啲特殊情況即係長方形嘅另外就係 hydrostatic force on curved surface， 咁就會係佢嘅做法咧，就通常係界呢個 liquid block 出嚟做一個分析就會係通過分析呢度佢上面啦側面啦同埋佢自己嘅呢一個嘅 force 去 analyse 究竟呢一個嘅 curved surface 嘅受力係點樣嘅通過力嘅平衡。通過力嘅呢個嘅中和 去計算翻呢一個嘅curve surface 嘅 force 嘅。咁另外咧就呢度 vertical 上面咧有可能咧，譬如話呢個嘅Fy 同埋 W 咧都係向下嘅，亦都有可能咧係 Fy 同埋 W 咧係向上即係相反方向嘅。咁呢個時候咧遇到呢咁嘅情況咧，即係譬如話呢度都係啦。如果呢一種情況咧，我哋去界呢個 liquid block 嘅時候咧，就會係界呢一嚿出嚟。計算個 horizontal force 嘅時候咧，就係呢邊 FH 啦，就係呢個面啦去計算嘅。而 Fy 咧就有兩個 pressure force， 一個係由上向下，一個係由下向上嘅，同埋佢嘅 self weight 就會有兩種嘅方法咧去呢度有兩種方法計算嘅，一個咧就係用liquid block 嘅上下表面同埋佢 self weight 嘅呢一個嘅 pressure force 加埋 self weight 嘅呢種計法，計佢嘅 Fv。咁呢度 Fv 咧就會係等於 Fy2減去 Fy1減去 W 即係會咁。另外一種計法咧就係咧，我哋理解到咧，就係呢度其實咧佢呢埲牆咧，你可以當佢係延伸落嚟嘅，而佢呢個嘅形狀咧就似係咧呢一橛嘅水咧就被滑走咗，就好似被替換咗。咁被替換咗即係有啲似係你擺咗一個空嘅吉嘅一個嘅容器入面去呢個水入面。咁佢所以呢度形成咗呢個嘅 buoyant force 就會形成咗一個 buoyant force FB buoyant force。咁呢個 FV 咧其實咧就亦都等於呢個 FB 嘅。咁呢度 FB 咧就等於呢邊嘅呢個 void 嘅volume 就 rho 呢個 fluid 啦 ，rho GV submerged 啦，即係 submerged 嘅 volume 去計算嘅。呢兩個咧係相等嘅 ，just the same 嘅。咁所以咧會有呢種情況下咧會有兩種嘅唔同嘅計算方式就通常如果個形狀比較複雜嘅時候咧，用buoyant force 咧係會快好多嘅即係有兩種方式。我哋嚟緊可能都會有啲 tutorial 或者係有啲嘅 assignment question 咧，都會講解俾大家即係會大家會可能考慮到嘅呢個係 static force 方面啦即係 fluid static 方面。咁跟住呢 buoyant force 頭先我哋都有提到啦咁equation 咧就係個 density 乘翻 fluid 嘅 density 乘翻 gravity 乘翻個 submerged 嘅 volume 後邊嗰啲就唔使理佢啦OK，咁跟住 fluid dynamic 呢度咧，我哋主要係講咗呢個嘅 Bernoulli equation。Bernoulli equation 咧有個 summary 嘅 OK。Bernoulli equation 咧，我哋主要係講緊佢係有呢個前設條件嘅。個 fluid 咧係要喺個 streamline 上面嘅流動，同埋個 velocity 咧係 steady 嘅情況下咧，先至係成立嘅呢個Bernoulli equation。即係因為 Bernoulli equation 咧係冇考慮 head loss 呢樣嘢嘅，冇考慮啲 energy input output 嘅嘢嘅。咁所以 Bernoulli equation 咧淨係考慮呢個嘅一啲嘅head 嘅變化。咁佢呢度咧就係喺呢個 equation 咧 Bernoulli equation 咧其實就係喺 hydrostatic equation 基礎上咧加咗一個嘅 velocity head。咁佢係考慮咗即係其實就係亦都可以從能量嘅角度去理解咧，就係有一部分嘅佢係動能同埋勢能之間嘅一個嘅轉變即係如果呢個 system 係冇 energy loss 嘅時候咧，佢哋兩個咧係相等嘅咁好多時候咧喺一啲嘅即係比較細嘅空間入邊咧，佢呢個咧係比較好用嘅 Bernoulli equation 譬如話即係話係一啲嘅 fluid 嘅 measurement fluid 嘅 measurement。 哋依家之前咧有個我哋講過有一種叫做pilot tube 或者叫 pitot tube 嘅喉 ，OK， 咁咧佢係當呢度有水流喐動嘅時候咧 ，OK， 咁呢度有水流喐動嘅時候咧，佢去到呢個嘅 pilot tube 嘅時候咧，呢啲咁嘅對住個水流嘅方向咧叫 pilot tube。pilot tube， 或者有啲叫做 pitot tube 嘅其實都係類似嗰啲嘢嚟嘅。嗱咁呢度咧就我哋去睇翻啦嚇，即係如果呢個水流係呢個咁樣方向行啦，咁如果我哋呢個係一個叫做 location 0、location 1、location 2。咁我哋去寫呢個 Bernoulli equation 嘅時候咧，咁就變咗都係呢個 P1 over 加碼加上 Z1 加上 V1 二次 over 2G 等於 P2 over 加碼加上 Z2 加上 V2 二次 over 2G，OK。咁喺或者寫上少少。P1 over 加碼加上 Z1 加 V square over 2G 等於 P2 over 加碼加上 Z2 加上 V2 over 2G 佢呢個位咧首先從即係 Bernoulli equation 或者 energy equation 嘅用嘅方法咧，就係基本上係先列舉咗成條 equation 出嚟，跟住再睇下有冇啲嘢咧係可以簡化或者 cut 咗佢嘅。因為 Z1 location 1同埋 2咧都係同一個高度嘅，咁所以呢兩個咧係互相 cancel 嘅。咁V1 就未知啦V2咧就係一個 zero 嘅，因為佢喺呢個嘅 tube 嘅呢個入口呢個位嘅。咁佢呢度入邊嘅 liquid 咧，咁呢入邊嘅 liquid 咧係靜止嘅，咁所以喺location 2呢個位咧，個 velocity 咧係 zero 嘅即係我哋就係喺個 tube 嘅呢個入口呢個位，個 velocity 咧係 zero 嘅。咁所以咧呢條式咧就剩低咧就係P1 over 加碼加上 V1 嘅二次 over 2G 等於 P2 over 加碼，即係咁啦。好啦，咁 P1 over 加碼咧就係乜嘢咧？就係呢度就係呢個高度。如果我哋將呢一個高度係假設係 A 細 L 咁樣啦，就係呢個高度。咁而 P2 咧 point 2嘅 pressure 咧就唔係呢度去剩咁少啦，佢就係由呢度計算落嚟㗎啦，呢度計算落嚟㗎啦咁如果呢一段咧個高度咧係 L， 跟住上面呢段咧係個 H 嘅話咧，咁呢度就係 L 加上 V1 嘅二次 over 2G 等於H 加上 L 咁因此咧呢個 V1 咧就會係等於咧呢兩個 L 咧 cancel 咗嘅，咁所以 V1 咧就等於根號 2GH 嘅咁就係如果我哋用一個咁樣嘅 pilot tube 或者叫 pitot tube 去度呢個嘅向住啲水流去度咧，咁我哋見到佢個 tube 入邊 over 咗呢個 water surface 嘅嗰部分嘅高度咧，就係代表住佢嘅 velocity head 嘅高度啦咁而個 velocity 咧就可以用根號 2GH 去計算嘅。咁呢個 pilot tube 或者 pitot tube 咧喺現代嘅雖然呢啲係好經典嘅，通過物理嘅方式咧去量度嘅。你會見到咧，即使依家咧即係去到現代咧，除咗呢一啲嘅即係我哋依家好多電子設備啦 嗱，呢一啲咧就係裝喺飛機度嘅叫 pitot tube 啦嚇。咁因為呢 pitot 呢啲物理嘅測量嘅方式咧，佢係非常之可靠嘅嚇，因為佢譬如話電子嘅設備啊、機械式嘅設備啊，佢都有可能係某程度上唔知咩時候咧會 fail 噶嘛。咁但係呢啲係唔會噶嘛，因為佢嘅原理咧係擺喺度嘅嚇，而嗰個結構咧係非常之簡單嚇，咁所以就佢係比較可靠嘅。咁所以咧呢種咧我哋即係通過呢一種方式咧去測量咧佢嘅呢個嘅因為有時候咧你用啲電子嘅儀器去度咧個水標啊咁樣啦嚇，咁你度嗰啲 pressure 啊或者 velocity 嗰啲 flow rate 啊，你都要 cal 過嗰嚿嘢先準㗎嘛嚇。
佢呢個例子咧，佢流佢啲水睇下咪同一個速度流動緊先至有效。
同呢個速度流動緊，咁你係你係放喺嗰個樓體度㗎嘛，係啊，咁咪就係度，其實佢就唔係度緊呢個位嘅速度嘅，佢係度緊佢對前少少嘅呢個位嘅速度嘅，其實嚇。咁所以
即係1、2點1格幾多都係
佢就咁你要睇下你個樓體係咪叫做 uniform 啦。咁如果譬如話你依家係一個 contraction 咁樣嘅，咁你喺呢度度同埋呢度度當然係唔同。咁當然你要去到一個比較 uniform 嘅位啦，即係譬如話一條直嘅批入邊，咁你喺呢度度同埋呢度度咧，基本上就係一樣啦。即係呢個亦都你頭先問嘅問題都係非常好嘅。咁咧就當然你要睇下你要測量嗰個位，你測量嘅目的係想睇乜嘢嘅嚇。咁如果你譬如話你即係需要知道佢一個 uniform 嘅一個嘅 velocity 咁你就喺一個比較速度比較穩定嘅地方去度咯。咁亦都有啲咧，你有啲地方有啲時候咧，你係想通過呢啲 tube 咧去度唔同嘅 location 嘅嗰個 velocity 嘅變化嘅，咁咧就會係譬如話喺 wind tunnel 入邊啊，我哋喺 water tunnel 入邊咧，我哋呢啲 tube 咧都會係移上移落去度嘅，因為佢可能唔同離開個 boundary 唔同咧，佢嗰個 velocity 咧有可能係different 嚇。咁另外咧喺呢度咧就頭先都有提到兩個嘅 concept 啦，一個叫做 steady 啦，一個係 uniform 啦。大家知唔知呢兩個字嘅喺 fluid 入邊嘅理解係乜嘢咧？乜嘢叫 steady？乜嘢叫 uniform 咧？佢係講緊邊方面咧？譬如話 steady flow 係乜嘢意思咧 ？uniform flow 又係咩意思咧？
速度變化，速度嘅變化。
OK 嗱係非常好嗱，呢兩個詞咧都係講緊速度嘅一啲嘅變化嘅咁 steady 同埋 uniform 係講緊邊方面嘅變化咧？兩個都係個意思都係穩定啊、好均勻咁嘅意思㗎嘛，係嘛
？steady 係 over time 佢 distribution。
Yes。
uniform 係喺個 over volume 或者 over 一個 area surface 上面佢係一致。
係啦，冇錯，非常好啊！呢個詮釋好好啊。咁咧 steady 咧就係叫穩定啊嘛。咁uniform 咧係均勻啊嘛，係嘛？咁所以 steady 咧佢嘅如果係一個 steady flow 咧，就係用數學語言去表達咧，就 du over dt 咧就等於0。咁即係話係時間嘅 dimension 上面咧個 velocity 咧係穩定嘅即係即係佢唔會佢呢個咧通常就係睇 local 嘅某一個位、某一個 point 上面嘅咁所以佢係 base on 某一個 point 上面嗰個 velocity 有冇 varying。咁呢個 velocity 咧，因為佢係 vector 嚟㗎咁佢如果 velocity 有方向或者係有大小嘅變化咧，佢都唔叫做 steady flow 㗎啦，即係 steady 係with respect to time 嘅 ，OK，with respect to time 嘅即係呢個係with respect to time 嘅，咁然後跟住咧uniform 咧就 with respect to location。 係、如果係 uniform flow 咧，佢個 flows 即係喺一個佢嘅呢個 system 入邊咧，個 velocity 咧喺唔同嘅 location 咧，佢係相等嘅嚇。咁我哋譬如話，如果一個 steady 嘅 flow， 有一種情況係兩種都可以係滿足嘅 steady uniform flow 嚇。咁通常如果steady uniform flow 咧，即係話佢既係喺時間上面係穩定，而個地方上面咧佢都係一致嘅。譬如話最簡單嘅，即係譬如話啲 flow 喺條直嘅批入邊嘅一個流動啊。咁咧佢呢度流動咧，佢個 velocity 咧係 v1 等於 v2嘅嚇。咁呢啲係好常見嘅嚇。咁而有啲時候咧，譬如話佢啲 flow 咧係一個 expansion 或者 contraction 咧就呢度咧呢度譬如話1，呢度2咁樣嚇。咁如果佢係咁樣流動咧，因為個 cross section 越細咧，個 velocity 咧係越大嘅嚇。咁喺呢種情況下咧，就係 non-uniform 嚇。咁另外一種嘅 non-uniform， 呢種係 uniform 呢種係 uniform 嘅。另外一種 non-uniform 嘅情況咧，就係咧，譬如話佢係一個 rotation 嘅 flow， 佢係一種 rotation 嘅 flow， 即係佢好似係一個攪拌嘅情況下，佢個 velocity 嘅 speed 係一樣嘅，個 speed 係 the same 嘅，即係譬如話我哋呢度係 V1， 呢個係 location 1，呢個係 location 2咁樣啦嚇。linear speed 咧係一樣嘅，但係佢嘅 direction 係變化緊嘅，即係呢啲情況，呢種都係 non-uniform 嘅，呢種都係 non-uniform 嘅嚇。咁佢喺呢啲冇，即係總之係 non-steady 或者 unsteady 或者係 non-uniform 嘅 flow 咧，佢都會產生一啲嘅 velocity 嚇。即係如果係 unsteady 嘅話咧，呢度就未必可以就簡單地用一張平面圖去解釋嘅嚇。咁譬如話我哋有啲好多嘅例子係乜嘢咧？OK 嗱，呢度咧就係一個啲 simulation 啦嚇。咁我哋睇下呢個 simulation 咧，佢係 simulate 緊一個叫做 Kármán vortex streak， 係一個比較出名嘅啲渦旋嘅流動嘅。咁我哋是但即係喺呢個斯連達後邊咧，我哋睇嗰啲位咧，佢個 velocity 咧係不斷咁樣打轉嘅嚇。見到紅色嘅位咧就係速度快嘅。咁我哋定喺某一個位，喺我呢個 mouse 呢個位，譬如話咁，即係假設啦。你見到佢個 velocity vector 咧係隨住時間咧不斷咁有快有慢有上有下嘅一個變化嘅。咁所以呢度後邊嘅呢個嘅 flow 咧，係每一個 location 咧都係一個 unsteady flow 嘅嚇，即係類似呢啲叫做 unsteady flow。即係如果佢係個 flow 係即係喺時間嘅維度上面咧係有出現一啲嘅唔穩定嘅時候咧，咁佢就叫 unsteady 㗎啦嚇。咁所以大家要知道乜嘢叫做 steady flow， 乜嘢叫做 uniform flow 嚇。咁呢啲嘅定義啦嚇，啲 concept。跟住我哋上一堂課都回顧咗呢個嘅continuity equation 嚇。continuity equation 就主要就用嘅比較多嘅就係呢兩條式 即係呢兩條式嘅話咧，上面嗰條咧5.29呢條咧就係講緊即係一般情況下嘅即係佢有accumulation， 即係話呢個嘅control volume 嘅 mass 有可能會變化嘅時候咧，咁就要用呢條。咁其實就係基本上嘅原理咧，即係個 principle 咧就係你個 control volume 嘅 accumulation 咧就等於加上 outflow 減去 inflow 咧係等於 zero 嘅。咁如果將佢移去等號兩邊咧，就會係個principle 咧就係 accumulation 咧就等於 inflow 減 outflow 即係一個非常之即係 straightforward 嘅一個嘅 mass conservation 嘅 concept 咁跟住咧，如果係 pipe flow 咧，咁pipe flow 嘅話，因為佢 pipe flow 通常 pipe flow 嘅通常都係啲水咧係充滿晒個 pipe 嘅 area 個 volume 㗎啦，咁所以咧入水同埋出水咧係直接相等嘅咁就冇即係除非你係啱啱好開水掣同埋閂水掣嘅嗰啲嘅即係起動嘅嗰下咁如果一般情況下個 flow 係穩定咗嘅話咧，咁佢應該就係出水同入水咧係相一致嘅，即係咁樣咁跟住 conservation of momentum， 咁咧就係就出咗呢個嘅 momentum equation。咁 momentum equation 咧就用嘅方式咧就主要就係呢一種呢一個會用得比較常見啲嘅呢一條式咁而呢度咧，一般情況下我哋去睇嘅啲嘅 flow system 咧都係 stationary 嘅，所以呢一嚿 control volume 入邊嘅 mass momentum change 我哋基本上都係 zero 㗎啦咁主要係睇 outflow 嘅 momentum 減去 inflow momentum 係等於翻 add 喺呢個 control volume 嘅 summation force 嘅大小嘅即係一個嘅 momentum 嘅變化。咁呢個亦都係 Newton second law develop 出嚟嘅一條嘅 equation Newton second law 多數係用喺一啲嘅solid 嘅 mechanics 入邊嘅，咁而家呢一條 equation 咧就係用喺啲 fluid 嘅 mechanics 入邊嘅咁呢條式咧要應用咧就係個要求咧就係你要畫咗呢兩個 diagram 嘅如果需要計算嘅話咁就需要分析個 force 嘅有咩 force 咁跟住咧就係 momentum 就係分析翻有啲咩出入嘅 momentum 咁跟住分開咗 x y 或者仲有 z direction 去分析翻嗰啲受力就咁樣咁呢條係momentum equation。跟住我哋亦都係回顧咗呢一個嘅 energy equation 就係呢條嘅呢度咁 energy equation 咧要即係呢個就個玩法上就好多啦就首先就係有啲似係 Bernoulli equation 啦，就係個 fluid 本身嘅 internal 嘅一啲 energy 即係唔叫 internal， 即係佢自己自身嘅一啲嘅 energy。因為如果講認真啲 internal energy 係另外一樣嘢嚟嘅internal energy 係個thermal energy 嚟嘅咁佢個 fluid 嘅本身嘅 mechanical energy， 即係 potential 嘅 energy 加埋呢個嘅 kinetic energy， 再考慮翻咧呢一個嘅 system 可能有泵嘅 input 或者有 turbine 去 extract 呢個 energy 出嚟。咁亦都會可能有一啲嘅喺流動過程中咧有一部分嘅 energy 咧 mechanical energy 咧係轉化咗去 thermal energy 嘅，咁咧就係屬於係 loss energy咁呢度有 alpha 1、alpha 2咧就一般情況下就 take 1就 OK 啦咁如果題目好特別要求咧，你就通常 assume 係1嘅。處理好多水嘅問題嘅時候咧，我哋基本上係攞1嚟去計數嘅咁head loss 咧，我哋會係後面嗰個 chapter 咧，我哋會講一啲嘅 head loss 嘅計算嘅 equation。head loss 有好多種唔同嘅 model 去計算嘅。喺open channel 同埋喺 pipe flow 咧，個 head loss 嘅公式咧都有少少唔同嘅咁跟住如果我哋知道咧係一啲嘅 我哋計算一啲嘅泵啊或者 turbine 嘅 energy 嘅時候咧，我哋就需要用呢條 power equation 咧去 estimate 佢需要幾多泵嘅 power， 或者係會產生幾多 turbine 嘅 power 嚇。咁呢度咧係會涉及到我哋嚟緊有一個 chapter 咧講緊一啲嘅應用嘅嚇，咁我哋會講個泵嘅 system 嘅嚇，點樣去 estimate 啲泵嘅。咁另外咧就係、一啲嘅 energy grade line 啦，同埋 hydraulic grade line 嘅畫嘅方式啦嚇。佢哋嘅區別咧就係、一個係有 velocity head， 一個係冇 velocity head 嘅嚇。咁所以如果當啲 fluid 咧喺條uniform 嘅 pipe 上面入邊流動嘅時候咧，佢哋兩個咧係EGL 同埋 HGL 咧係兩條平行嘅線嚟嘅嚇。如果係有泵嘅情況下咧，EGL、HGL 咧就會一齊咧係有泵 energy 嘅 input 咧，泵 head 嘅 input 咧係 suddenly increase 嘅。咁如果有 turbine 咧就 suddenly drop 嘅嚇。如果有遇到一啲嘅變 pipe 嘅變diameter 嘅情況咧，就會係睇下個 velocity head 咧就會有變化啦，同埋個 slope 嘅 gradient 咧，亦都會因應個 velocity 嘅變化咧，係會係有一啲嘅相應嘅改動嘅嚇。咁如果個 velocity head 越大咧，個 slope 咧就越奇嘅嚇，越 steep 嘅。咁呢啲我哋上一堂課嘅回顧啦。Okay? So for the main content for this lecture, we start from the topic 2. Okay. So for tonight, we are going to talk about the some contents about the hydraulics, and the first half of this module is about the hydraulics. Hydraulics is mainly talking about the two aspects: the pipe flow and the open channel flow. Alright. So from the topic 2 is firstly talking about the pipe flow. I think that most of you may have already learned something about the pipe flows ideas, okay, in the previous fluid mechanics content. So maybe for the general pipe flows part, I will go a little bit faster, okay. So for the pipe network, okay, I will spend more time to talk about the pipe network, how to do the pipe network design principle, and also the how to estimate the pipe network's flow in each pipes in the network. And then firstly, the concept about the laminar flow and the turbulent flow. The laminar, okay, this name is very similar to the worst layer, okay. So that's it is talking about that in the laminar flow, the flow is just like very regular, okay. The flow is like very regular. The flow is not mixed with the other layer. So that for the laminar flow, in this video, the velocity, there is a flow in the transparent tube, and the solid line here, okay, the black line in the middle is actually we call the straight line, which is using the diode to visualize the flow. All right. Now, in the video, the flow of the fluid will increase from the velocity will increase gradually. You can see that what will happen for the line in the middle. Okay. So in the very beginning, the velocity is small, so that the line is very stable. And then when the velocity increase, you can see that in this status that the flow become unstable and appears like the mixing pattern. Okay, now in the very beginning, we can see that the flow is moving. All right. However, there is very limited mixing pattern for the fluid. So the flow is flowing like layer by layer, and the fluid particle you can consider is very regular. Okay. Now, when the velocity increase, you can see that the diode become unstable. Okay, the straight line become unstable, and this is sometimes we say it is a transitional or the unpredictable flow pattern, okay? And later we can see that the flow start doing the rotational motion. Actually, it is rotating and moving. Now, just like the volcano vortex strip, okay? Actually, the flow is rotating and moving forward. Rotating and moving forward, okay? So that this is rotational flow. And then when the velocity become faster and faster, you can see that the diet become very difficult to identify it is a line, okay? Because it mixes with the transparent fluid very quickly and thoroughly. And when the velocity is fast enough, you can see here, you can even though cannot see any image about the diet, okay, and the strict line. So this is from this kinds of the situation, it is already in a very fully turbulent situation, okay, fully turbulent situation. So that we can see it again, okay. So the laminar flow to the turbulent flow, okay, it is based on different regime of the flow and very close to the velocity of the fluid. However, velocity is not the main things for the control because the velocity also need to combine with the viscosity and also the diameter, okay? If only talking about velocity is not accurate because sometimes for the water and for honey, okay, if they are running on the same velocity, for example, the water may get into the mixing pattern very quickly because water has a low viscosity, but the honey has a very high viscosity. If the honey is also running at the same speed of the fluid, they may not appear like the mixing like this, okay? So that for determine the laminar and the turbulent flow, it is not just considering the velocity, but we will use, okay, now here in this figure also talking about the same thing. For the figure 8, for the part A, it is the laminar flow. It is clearly see that the line, okay. For the figure B and should be figure C and D, it appears like the mixing and the sometimes the rotational flow pattern, okay. Now, to classify the flow in the laminar regime or the turbulent regime, we will use the famous non-dimensional term, or we can sometimes say it's a pi group. Okay, a pi group. A pi group is a dimensionless group. Dimensionless. Okay, the pi group is also named as a dimensionless group. Now, we can see that in the modeling, we use quite often that using the dimensionless group for finding the relationship between the parameters. Okay, this is based on the dimensional analysis. We try to use the dimensionless group to minimize that the relationships. Okay, now the Reynolds number. Okay, the Reynolds number, it is RE subscribe D. Okay, the Reynolds number is not only used for the pipes. Okay, it can be used for many scenarios that related to the fluid. So that the Reynolds number is mainly, there are four mainly calculation equation. Vd over nu, okay, Vd over nu, or rho Vd over mu, okay. We mainly use these two. Now, phi is the velocity, very clear, okay. V is the velocity, d is the diameter. Okay. I think this is very clear. Now, this is something very similar to V, but it's a squid symbol. It's new, okay? This is new, it's not V. I'm not sure that whether some of you play Gundam model before. High new Gundam, okay? Do you know what is the 海牛高達有冇聽過 ？High new 高達就係呢個。Okay, this is new. This is new, okay, pronounced as new. So it is a Greek symbol. It is in, yes, both this mu, okay, this mu, both are viscosity, but this is a kinematic viscosity. This is a dynamic viscosity. What's the difference? Their relationship is the nu is equal to the mu divided by the rho. Rho is the density, you know. Okay. Their relationship is like this. The viscosity will affect that the viscosity. Now, the kinematic viscosity, the unit is usually the meter square per second in the SI unit. The dynamic viscosity is Newton second per square meter, or sometimes simply the Pascal second. Pascal second. Okay. Now, for a very easy remember value is that the mu of water in 20 degrees Celsius is equal to 10 power minus 3 ns per meter square. And the nu for water also at 20 degrees Celsius is 10 power minus 6 meter square per second. So, in this equation, the Reynolds number is calculating the Vd over nu, or rho Vd over mu. They actually talking about the same calculation. Now sometimes if you don't use the velocity, you may use a Q to replace the velocity for this calculation. So there are four calculation equation for the Reynolds number, but most of the time we use the first two. Okay, we use the first two. Now the viscosity affects that we say the flowability of the fluid. If the viscosity is high, that means that the fluid is very difficult to flow, okay? Or the resistance is high when it's flowing. Now, in the fluid mechanics, we have introduced that the Newtonian fluid, okay, and the non-Newtonian fluid. Now, Newtonian fluid is talking about that if the fluid follows that in this figure, okay. Now, if there is an equation, we say the Newton's laws of viscosity, but it's not the main thing here, okay. Newton's laws of viscosity. Nu is equal. Shear stress is supposed to be a shear stress is equal to nu times d velocity over dy. Okay, Newton's laws of viscosity. This is talking about the shear stress for the flowing fluid. Okay. Now, if fluid follows that Newton's law of viscosity, that means du over dy, and the shear stress is on a linear relationship, the straight line. We call this is a Newtonian fluid. If it is not linear, it is non-Newtonian fluid. The other ones, okay. There may be the latent fluid, or pseudoplastic fluid, or plastic fluid, okay. Or sometimes we say this is a shear thinning, and this is shear thickening, and this is the Bingham plastic fluid, okay. Now some of the example can be like in this video, just for information for this part, okay. It's not for the main content. It's interesting. Now we can usually understand that the low viscosity fluid is mainly the Newtonian fluid. For example, water, the oil, the honey in not a very high concentration situation. The air are supposed to be most of the common fluid that in our daily life is the Newtonian fluid. Okay. Some of the now this is the liquid honey, but the viscosity, the concentration is not that high. Okay, so that is like it's not flow like the water. Okay, so that but if the honey, okay, if the honey is in a very high concentration, it will become a shear thinning. Okay, shear thinning, just like the toothpaste. Okay， 好似牙膏嗰啲都係類似係呢啲嘅 non-Newtonian fluid。佢 non-Newtonian fluid 呢個 shear thinning fluid 咧，佢嘅特徵咧就係咧，你要即係譬如話你要將呢個 honey 倒出嚟咧，你同倒一杯水係唔同嘅，你係需要咧係將佢傾斜得多啲嘅，即係話要俾一個大啲嘅 shear force 佢咧，佢先至會 flow。好似啲液體咁樣 flow 嘅。如果你嘅俾嘅 shear force 咧唔夠大咧，佢就未必係個 flow 咧未必咁即係個流動性未必咁好嘅。OK。另外一種咧non-Newtonian fluid 咧就類似呢啲嘅好結塔塔嘅咁樣嘅一啲嘅，佢其實就唔係一種又唔係一種溶液，就好多時候係一種嘅類似嗰啲膠體狀嘅嘢即係我哋常見嘅。如果喺工地咧，你都好常見嘅一啲嘅石膏嘅石膏嘅水同埋石膏嘅混合物咧，佢係屬於係一個 non-Newtonian fluid。其實英泥都係，即係如果係啲即係未乾嘅石屎啦即係都係屬於係 non-Newtonian fluid 嘅 shear thickening。呢個叫 shear thickening。佢嘅特點咧就係你用一個比較細嘅 shear stress 嘅喐佢嘅時候咧，佢會係流動性係比較似係 fluid 嘅。但係當你如果用一個比較大嘅 shear stress 去衝擊佢嘅時候咧，佢反而咧就會冇咗個流動性嘅，因為佢嘅分子嘅分佈咧，當接受緊大嘅衝擊力嘅時候咧，佢嘅反作用力咧係相對比較大嘅，即係好似咁樣咁呢種係另外一種嘅non-Newtonian fluid。呢度 for 大家 information。So because the viscosity is also used for the calculation in the following content, so I just would like to refresh you some memory about the viscosity. Okay. Now, but viscosity we can find in some handbooks or in some figures or or diagram, but most of the time in this module I would directly tell you, okay, for this for the fluid in certain temperature, okay. Now the Reynolds number is a number, so this has no unit, okay, because it's a dimensionless group. So if the Reynolds number is smaller than 2000, it is classified as the laminar flow. This is talking about in pipe flow, okay, in pipe flow. RED is mentioned in the pipe flow, okay. Now in the open channel flow, the number is not like using the 2000, okay, or in the groundwater is not using 2000. This number, this value to determine the laminar flow and the turbulent flow is talking about in the pipe flow, okay, in the pipe flow. Now, developing flow and developed flow is just for information as well, okay? Because sometimes when the fluid flowing from one section to another section, there must be a distance that the fluid's velocity profile is changing from one to another, okay? Now, for example, if the fluid flowing from a tank to a pipe, okay, initially the velocity entering this entrance, it is very uniform distribution. However, because of the boundary layer, okay, because of the boundary layer or the friction from the boundary, so that the velocity will start to develop a very significant boundary layer, and making that, all right, here we need to talk about a concept. It is the no-slip condition. 大家知唔知咩叫 no-slip condition 啊？對呢個名有冇啲咩印象啊？boundary layer effect，OK， 係嘅啊。boundary layer 嘅話咧，就係喺呢個 boundary layer 呢個位咧，佢好得意喎，即係個 fluid 喺個 solid boundary 呢度咧，佢嘅 velocity 咧係等於零嘅，啊，即係話係 just at 呢個 boundary layer 呢個位咧，佢係冇 velocity 嘅，啊，個 velocity 等於零嘅。嗱，咁 no-slip condition 咧可以通過呢一個video 咧去驗證嘅。嗱，咁呢度係呢張呢個 video 咧就係黃色嘅地方咧就係喺一個 channel 入邊嘅，咁咧啲水咧就係由呢個右手邊咧流去左手邊嘅，係一個咁樣嘅流動方向嘅。咁呢一支黑色嘅呢一支針咧，佢就係 inject 一啲 dye 啊。咁咧佢依家咧係黐住，即係懟到落去個 channel 嘅底部嘅，去 inject 呢個 dye 嘅。啊，大家留意下咧。嗱，咁佢 inject 呢個 dye 咧，嗱咁佢依家離開咗啦。咁就佢一部分嘅 dye 咧就係喺呢度 inject 嘅，咁另外一部分嘅 dye 咧就係隨水漂流嘅。咁佢離開過呢個底部嘅，咁離開呢個底部咧，咁佢會喺呢度咧，嗱，咁兩種嘅唔同嘅狀態啦。咁隨住呢個時間推移啦，咁佢離開個缸底嘅呢個部分嘅 dye 咧，佢係隨住呢個嘅液體咧係流動嘅，但係喺底部咧，你見到佢個流動咧係有一部分嘅 dye 咧 particle 咧。係基本上係黐住咗喺底部嘅，佢基本上係冇喐嘅。佢而呢個 dye 咧並不是係held 咗喺上面，即係唔係好似油漆咁樣係黐實咗，即係唔係化學嘅作用咧黐咗喺度。佢只不過係呢個 particle 咧喺個底嗰度咧係冇 velocity， 所以佢就好似 settle 喺度咁樣啦 ，settle 喺度嘅。咁點驗證佢係 settle 喺度定係黐咗喺度咧嚇？咁佢等間咧會用一支筋咧去搞佢嘅嚇，咁佢咧搞佢之後咧，佢就走咗啦。咁即係話呢 particle 咧， 並不是係好似啲即係油污咁樣黐咗喺度，佢只不過係 settle 咗喺個底部。點解會 settle 咧？係因為個底嗰度咧個 velocity 咧係等於零嘅。咁呢個就係所謂嘅 boundary 所謂嘅 low slip condition 啊。low slip condition 係講緊咧就話喺呢個 flowing fluid 嘅時候咧，佢個 boundary 咧個 velocity 咧係等於 zero 嘅。即係個 boundary 即係 solid boundary 嗰個位咧個 velocity 咧係等於 zero 嘅。咁咩叫 boundary layer 咧？我哋都睇一個 video 咧，要去睇翻呢個 boundary layer 係咩嚟嘅。咁我哋睇下啦，就我哋睇到咧呢度呢個啦。咁呢個係一塊好薄嘅 plate 啦嚇。咁跟住咧，佢呢度 jam 一啲嘅 hydrogen bubble。咁咧你見到咧喺呢個前端咧，佢會界開咗呢一紮嘅hydrogen bubble 嘅，即係白色嘅嗰啲嘢嘅。咁咧就會係當佢喺呢個plate 嘅呢個表面嘅時候咧 velocity 係零。咁但係呢啲 bubble 係喐緊㗎嘛，咁所以佢一定係會有一個嘅區域咧係由零嘅 velocity develop 去一個佢依家嘅喐緊嘅uniform 嘅 velocity。大家望下咁就係會形成咗呢一個少少好細好薄嘅一個 layer 咁呢個 layer 咧個 velocity 你見到佢呢度咧係零，因為零 velocity， 所以佢呢度咧係如果 hydrogen bubble 係喐緊嘅話咧，同一時間喐嘅話咧，佢呢度咧就會係應該呢度係會見到白色嘅，咁但係底下呢度冇嘅。咁即係話呢個位咧就係冇 hydrogen bubble 喐過嚟嘅。咁但係呢啲 hydrogen bubble 係喐緊㗎嘛，咁所以咧佢會係拉扯住咧有一個呢一個 boundary layer 度咧，就係由零嘅 velocity develop 到去佢某個速度嘅 velocity 啦。咁所以呢個就係個 boundary layer。咁而呢度咧亦都睇到個 low slip condition 嘅情況嘅。咁個 boundary layer 咧，雖然佢係一個好薄嘅一浸，但係佢係形成咗呢個嘅head loss 嘅一個最主要嘅地方即係形成咗呢個 velocity 同埋 energy loss 嘅一個最主要嘅地方佢之後咧有個係隨住佢嘅變化啦。咁呢度嘅呢個 video 咧就睇到呢個 boundary layer 咧會變得越嚟越厚嘅。但係又唔會無限咁厚嘅 ，OK， 即係佢會係沿住呢個嘅 plate 嘅一個前端位咧，佢 develop 落去咧，就係一個越嚟越變厚嘅一個嘅情況嘅。大家再睇多次。佢會係由薄嘅，跟住慢慢變厚嘅呢個 boundary layer 咁係因為佢去到後邊咧，佢個呢個嘅原因係因為佢產生咗一個 friction， 呢個係呢個 stable 嘅，即係叫 stationary 嘅 plate， 跟住喐動緊嗰啲白色 bubble 咧，佢係屬於係嗰啲有 velocity 嘅咁佢個 boundary layer 咧會越嚟越厚嘅咁但係又唔會無限咁厚到一定程度咧，佢就會係比較 stable 啦因為佢形成咗個平衡形成咗個平衡。So when we come back to this figure, so that it is when the fluid flowing from a tank to a pipe, actually they forms the boundary layer, okay, boundary layer. So the boundary layer become thicker and thicker, and so that making that the velocity changing from 0 to a certain value, okay. So that finally the flow will become very stable velocity distribution. We say that in this region is a fully developed flow, and this region is developing flow. Okay. Now, why do we need to know this small area and the distance? Usually, sometimes you are asked now here is the estimation of the entrance length distance, okay, entrance length. How long will this development flow develop? Now this is sometimes used for your consideration if you are asked, okay, to meter to measure the flow or measure the pressure. Okay, if you are installing the meter in this region, okay, the flow may be unstable. Okay, the flow may be unstable. So that's sometimes that this velocity profile may not be very representative. Okay, so that you may consider to install the meter, for example, the flow meter, in this developed flow region. Okay, this is more preferred, so that this will make your measurement of the velocity or the flow will be more stable, and more the data will be more stable and more useful. Okay, so this is the now when you are going to buy a measuring device, for example, pressure meter, the flow meter, usually it will ask you, okay, it will ask you that install, for example, if you have a pipe section, okay, to install the meter, okay, sometimes we buy the flow meter, they will ask that you may need to have 10D distance away from the previous transition, and maybe 5D, okay, 10D and 5D away from the next transition, okay, to make sure that this flow measurement is stable. Okay, 10D and 5D, it means that the D is the diameter. Okay, so that it will help you to find a better location to have a more accurate measurement of the flow. Okay, so this is the what the entrance length is used. Now next is talking about some introduction about the pipe size. Okay, the pipe size. Sometimes when you have done some calculation of the necessary diameter, however, it is not able to exactly ask the manufacturer to manufacture or produce a pipe size that according to your necessary diameter. So that sometimes you need to refer to some commercialized product, okay, from the supplier. So usually you may use the DN pipes to do the to buy this kinds of material for the design. Okay. Now the DN is kinds of the standard diameter in most of the countries. Okay, so it controls the outer diameter mainly. Okay, it controls the outer diameter, so that the DN pipes, the outer diameter must be the same or very tiny variance. However, due to different schedule or the wall thickness, the inner diameter may vary. Okay, so that when in your calculation, the inner diameter is the thing that you calculate. However, okay, you may need to determine what kinds of the wall thickness of the pipe you are going to use, so that you will, where you have done, for example, you have done a necessary diameter of 20, the necessary diameter D in the calculation is 200 mm. Okay, it's necessary. Now, actually, the 200 mm is very likely the DN200 pipe. Now, but the DN200 pipe may, according to the manufacturer's manual or the catalog, all right, there may be the 40 schedule or 80 schedule for different wall thickness. Okay, different wall thickness will result in different inner diameter. So that sometimes if the inner diameter is less than 200, most of the time you will consider to use the larger size. For example, DN205, 250, okay, to fulfill that your necessary diameters requirement. And then you will use, if you think that the 202.7, this one is the one you select, you may use the 202.7 to do the calculation again for the head loss and other flows, velocity, to see what are what if you use this kind, you have select this pipe to in your system. Okay, so so this this kinds of calculation you need to refer to the manufacturer's catalog. Okay. Now, next is talking about the head loss in the pipe system. The head loss in the pipe system. The head loss is a very essential things that in our design or the calculation. Okay, because you see that in the energy equation, we pay attention to the flow energy and the energy input, for example, the pump and the turbine, and focus on the head loss. Okay, the head loss will determine that whether you need to use a pump or whether you how much turbine energy you can extract. Okay, the pipe flow's head loss is mainly contributed by the two aspects. One is the pipe head loss. Okay, the frictional head loss comes from the friction of the wall material. Okay, usually the wall friction. The component head loss comes from the fitting. Okay, comes from the fittings. For example, the valve, the bands, and the teeth. Okay, these types of the fittings in the pipe system. Some textbook may call this as the major head loss. Some textbook may call the component head loss as minor head loss. Okay. One is the major loss and the other one is minor loss, because sometimes, most of the time in the pipe system, you may have very loss of the straight pipe, but less amount of the bands or the joints or the valve. And usually, okay, the component head loss is sometimes less significant than the pipe head loss. Okay. So for different textbook may have different name. Mainly contribute by these two. Okay, for a pipe system, you may need to calculate pipe head loss and the component head loss and add together. Okay, to estimate the total head loss. Now here is the next content is talking about how to work out the equation for the frictional head loss calculation. Now, there are three models that we use quite popular, okay, in the head loss calculation. Now, one is the Darcy-Weisbach equation. Darcy-Weisbach equation has Darcy friction factor, the f, the small f. The small f is also a dimensionless factor, dimensionless group. It's 4 times the tau 0. Tau 0 is the wall shear stress. Wall shear stress. Okay, wall shear stress. The shear stress is linearly distribution. Okay, it's linearly distribution. The shear stress at the, or we may say it is like this. Okay, the shear stress as 4 is the maximum. At the center, the shear stress is equal to 0. Okay, at the center, at the center line, the shear stress is 0. Okay. Now, so the frictional factor is 4 times the wall shear stress over the kinetic pressure, rho v squared over 2 here. Now, but most likely, most of the time, we are not going to calculate in this way, but we will use a Woody diagram to look for the value for the frictional factor. Okay. Now, by the use of the frictional factor, we have the first popular equation in the calculation of the head loss is the Darcy-Weisbach equation. Similarly, we sometimes in some model we say the DW equation. Okay, the DW equation, the Darcy-Weisbach equation. Now, this equation is I think that this equation is has it's not so complicated. Okay, is the frictional factor F. L is the length of the pipe. D is diameter. V is the velocity. Okay, F is the friction factor. So the F is the Darcy friction factor. Okay. Now this head loss equation, Darcy friction equation, Darcy Weisbach equation can be sometimes modified to this format. Okay, KQ squared. Well, how to do this change? But this form will be used in the pi network system calculation. Now this is because that because in the pi network system we sometimes focus on the Q, the discharge. The velocity is equal to the discharge over the area of the pipe. If it's a round pipe, it's equal to pi over 4 times d squared, right? And if we combine these two equations, the HL, the head loss, is equal to the F L over D, Q over pi over 4d squared and square and over 2d or 2g. Now, after rearrangement, it will be equal to the 8FL over pi squared GD power 5Q squared. Okay. So it's using big K to represent this the calculation, this group of calculation. Some textbook may use R, okay? Some textbook may use R to stand for the group of calculation. Now, because in the pi network, okay, in the pi network, it is this kind of K factor is not changed very significant, okay. So that the change of the flow is mainly due to the head loss may be mainly affected by the Q, okay, discharge. So that this K factor is usually very stable. So they sometimes use this form, the KQ power n form, to represent the head loss. Okay. Now this is the Darcy-Weisbach equation. Darcy-Weisbach equation. In this module, I think that I'm not spending so much time on talking about how this equation is developed, but I have this part of content. If you want to know more about how this equation is developed, you can study by yourself. We may be talking about how to use this equation to do the calculations later. Okay. Now, another model for the head loss calculation is Hazen-Williams equation. Hazen-Williams equation. Okay. Sometimes it's also WH model, WH equation. This equation seems that the equation is not very, it's very empirical format, okay? Because the power form is not an integer number. It's 0.63, 0.54, this kinds of the factor. KH is unit conversion factor, okay? Unit conversion factor. C is the Hazen-Williams roughness. Here it has talked about that. C is the Hazen-Williams roughness coefficient. R is the hydraulic radius. SF is the friction slope. This equation is not directly for the calculation of, this is calculate the velocity, okay, to estimate the velocity. But this equation is for the Hazen-Williams equation head loss term. It is per 1,000 feet or 1,000 meter. Okay, depends on the unit you use. Okay, there is also a unit conversion factor, which is there is two format. Okay, A Q over C power 1.85, D power negative 4.87, or BQ C over C D power 2.63 power 1.85. These two equations, okay, this is putting the A outside bracket and D outside bracket, but this one is putting the A becomes a B into the bracket and D become into the bracket, okay, so that there are two formats. The A for the SI unit is 10,070. B is 1,400. B is 151 for SI unit. For the US unit, the B is 149. For US unit is 10,500 for US customary unit. Okay. Now C here is still the Hazen-Williams equations coefficient roughness, or we say the WH roughness. D is diameter for sure. Okay. Now for this Hazen-Williams HW, sorry, not WH, is HW. Hazen-Williams equation roughness. You can find this information from this table. According to different pipes condition and the new pipe or the old pipe, okay, the Hazen-Williams coefficient considers that the age of the pipe, and then this equation, this figure, the table, also lists out the Manning friction factor, Manning's roughness, the Hazen-Williams roughness, okay, and the KS. The KS is the surface equivalent roughness height for the Moody diagram, or for the Darcy-Weisbach equation. Okay, the three roughness comparison. For different pipe material, for ductile iron, okay, ductile iron is a very common water supply pipe that used for the main pipe, okay, in nowadays. Some of these are coated by the asbestos, okay, cement, or some of the casted by the epoxy, and see that whether there is any epoxy linen. Seems no, okay. Nowadays, sometimes we coat the ductile iron with the epoxy, so okay, so you may need to look for some international information, okay. Now, next is now the Hazen-Williams equation also can be converted into the KQ power 8 format. Because the discharge here is power 1.85, so that in using the Hazen-Williams equation, the KQ is power 1.85. The K is calculated like this. This phi is also the unit conversion factor for US unit and SI unit. Okay, L is the length of the pipe. Okay, in the feet in the US unit and the meter in the SI unit. Okay. The third model for the head loss estimation is the Manning equation. Many equation usually will use in the open channel flow or the drainage pipe. Okay. The many equations head loss calculation is seems that the model is very complicated. Okay, it's n square L over beta R power 4/3 and A squared and Q squared. Okay, n is the main friction factor. Main roughness factor. R is the hydraulic radius. Beta is the unit conversion factor. Okay. Beta is unit conversion factor. A is the area. A is the cross-section area. So in US customary unit, usually it is feet or this unit. Okay. In the SI unit, it's usually meter. Okay. Now, so that's the managed roughness is also can be found in this table. Can be also found in this table. Okay. Now we will have some. Okay, so here we have introduced the three models for the estimation of the head loss. Okay, the Darcy-Weisbach equation, the Hazen-Williams equation, the Manning equation. Three models. Okay, three equations for estimating the head loss. So later we will have some examples or tutorial question to show you that what's the difference to use these three equations to estimate the head loss. Okay. Now at this moment we may take a 10 minutes break and then we will come back at the 8:40 p.m. to continue the remaining content. 係啦，
打個二個街啦，
咁所以咧，你要係個計算埋啲嘅關出生率啊，收入啊，咁呢度同埋呢個 P 嘅數啊，咁佢就所以你呢個你要用個係啦，你要有嗰個收入條規出嚟，如果唔係就冇，就只有呢個。所以你多咁樣呢度其實係攞列佢出嚟係要列佢。
咁我諗下，其實我個 T 嘅上個作用就係翻 M 咁樣咯，即係佢只不過係攞兩嚿嘢，跟住兩即係煙嘅 water 同 out 嘅 water 咁樣整到連條線咁樣。咁去創一個新嘅關係出嚟，即係我哋翻 M 就係得咁。我覺得翻 M 錯啲 equation 嘅。
即係你要，
所以我
A 全方式就 solve 咗一個咩啊？
係當然啦，呢個即係 K 嗰個，但係佢最根本個，即係我哋最根點解佢會整個翻 M 呢一個數嗰個出就係要錯一啲 relation 先出嚟。咁你點錯啲 relation 就係好多粒，跟住揾佢哋之間嘅關係，跟住就錯到好多 relation 先出嚟，跟住就滿足到你最夠 equation 多，咁你個 equation 同個 equation 多過你暗東嘅情況，咁你就一定計到咯。只不過係好快，但係佢一定會計。
咁樣範圍有啲大。
係冇錯。
我係
安定同
我係完全放棄咗四分一咯，記唔到個 number。
咁你佢叫完全放棄，你放棄咗四分一啫。
係嗰四分一完全放棄，一見到咪就唔食，keep 咗。好嘅，喺老細搞我咁多，讀張對你讀。如果佢可以將 technical 幫我做 technical practice 我開心。雖然可能都係啲常得嘅。都會。
Okay, so let's come back to the lecture. Now previously we have introduced three equations to estimate the head loss. That one is the Darcy-Weisbach equation, which is very common, very popular in most of the time. All right. Now, but this Darcy-Weisbach equation, sometimes the frictional factor, we need to have some information to look for the frictional factor first. It's not only the pipe material, but we need to combine with the Reynolds number to look for the frictional factor, so that the Darcy-Weisbach equation to estimate head loss is sometimes it is not a very straightforward method. Okay, but the Hazen-Williams equation we just need to look for the table to find the pipe material. We can roughly estimate it, we can find the coefficient C, or many equation we find the Mannish roughness N. Then we can directly work out the head loss. Okay, there is no iteration procedures for the Hazen-Williams equation and the Mannish equation, so that this is why the Hazen-Williams equation and Mannish equation is also a very preferred method for some calculation. Okay. Now, mainly the Mannish equation is for the open channel more than the pipe flow. Okay. Now, here we have a concept about the hydraulic radius. Hydraulic radius. This part of content we'll talk about later. Hydraulic radius is for a non-round conduit. It's for a non-round conduit. Sometimes that the pipe section is not a circular, or sometimes that the cross-section of the flow is not a circle. Okay, so that we may need to have some calculation to refer it to the circular parameter. So the hydraulic radius, for example, a cross-section is not a circle, for example like this. We will use the area of the flow, the cross-section area, divided by the vector parameter. The hydraulic radius, RH, is equal to the A over P. Okay? The area over the vector parameter. The cross-section area over the vector parameter. Cross-section area over, or sub zone, is the length that in touch with water, which is vectored by the water. For example, in the open channel, it's talking about this edge that in touch with water. Okay, so this is the hydraulic radius calculation. There is also the hydraulic diameter. Hydraulic diameter. The DH is equal to 4RH, which is equal to 4A over P. Okay, this is hydraulic diameter. Hydraulic diameter. In the Darcy-Weisbach equation, if, for example, in this equation, if there is a non-round conduit, the D can be replaced by the hydraulic diameter for the calculation. And in the Hazen-Williams equation, it's also, if there is no D, okay, no diameter, you can use the hydraulic diameter to replace it. Okay. Now in the Mannish equation, it directly use the hydraulic radius for calculation. Okay. Now, next is talking about some, this kind of content is for your information, not necessary to, it's not, we will not use this part of content for main calculation. Okay. Now, the shear stress distribution in the round pipe is, after development, it is calculated like this way. It's R over 2 times the piezometric pressure gradient. So that means the shear stress distribution in a round pipe is like a linear distribution. Okay? It's like linear distribution. That is what I said. The shear stress at the wall is the maximum because the wall is stationary. The fluid is moving. Okay? So that the shear stress is the maximum in the wall. And it's 0 in the center. It will be 0 in the center. Okay, so you just need to know, have the information like this. You may know that the shear stress at the wall is the biggest, is the biggest, and then in the center is equal to 0. Nothing special. Okay. Now next is the velocity profile in the laminar flow. Laminar flow, that means the Reynolds number smaller than 2000, okay? The velocity distribution will be like this way. The maximum velocity is appear like in the center line. Okay? The velocity maximum will appear at the center line. And the velocity distribution in the laminar flow is on the manner of the parabolic, okay? Parabolic, because the R power 2 is on the parabolic manner, okay? Because it's one subtracts the radial location square over the R log, okay? So that it is a parabolic manner. This is, we will not use this directly for calculation, okay? So you just know the distribution is like this. That is enough, okay? Next is talking about that the relationship of the mean velocity and the maximum velocity. You will see that this is based on the mean velocity calculation. The mean velocity means that the Q over A, the discharge over the area in the laminar flow. In the laminar flow, the maximum velocity is just is 2 times of the minimum, 2 times of the mean velocity. Okay, the centerline velocity is 2 times of the mean velocity. So this is for the laminar flow in the pipe, in the round pipe. Okay. So that is enough. You just need to know there is such relationship. And also, okay, in the laminar flow, the frictional factor has a fixed, very clear relationship. Is that it is equal to frictional factor is equal to 64 over RED in the laminar flow, so that for the flow in the laminar pattern, the flow is more predictable because the flow is in very stable and very regular flowing pattern, so that the frictional factor is predictable, not like the turbulent flow. Okay, if the flow is in turbulence, most of the time, okay, we will use the empirical equation to predict it. So in the laminar flow, the frictional factor can be directly calculated by the Reynolds number. The frictional factor is related to the Reynolds number, right? So that's why I say using Darcy-Weisbach equation, the frictional factor is not directly worked out by the pipe material, but you need to sometimes combine with the Reynolds number to estimate. For the turbulence flow, which is the Reynolds number larger than 3000, the velocity profile is usually cannot be predicted by the deduction from the previous physical model. Okay, it is most of the time is estimated by the empirical model. Empirical model means that the scientists done lots of the experiment and summarize the coefficient for the distribution. Okay, so that's the empirical model. Usually, you need to look for the table. Okay, look for the table for the coefficient. For example, UR is equal to, if you can we make it to be a very similar format as the previous velocity distribution. The UR is equal to the U max times 1 subtract R over R log power n. Okay. Now the velocity distribution in the turbulent flow will be like can be expressed by this model, and the n value can be found in this table by using different Reynolds number, okay, and then look for the n's value. For example, here, okay. Now, now we can see that the relationship between the maximum velocity and the mean velocity is most likely 20% higher than the mean velocity for the turbulent flow. Okay, this is just for information. Okay, and it is not also the same. We will not directly use this model for the estimation, right? So this is so for this part of content. Some of the content is for information, so we go faster. Okay. Now this is talking about the boundary layers, viscous sublayers velocity distribution. Not very important, so we will not talk about in detail. But we will talk about this figure. Okay, we'll talk about this figure, and to analyze that the figures, what the figures and the research, the experiment data can tell us. Now we'll basically talk about 4 observations here. Okay. Now in the there are numbers of experiments done for different time material, for different material of the different sand roughness. Okay, and now in these figures that we can see the left hand side is the frictional factor F. The bottom is the Reynolds number. This right hand side is the relative roughness, Ks over d. Ks is sand roughness height. It is related to the roughness of the pipe material. Okay, d is the diameter of the material. Now, in this figures, that it's very clear that for the region, for Reynolds number 2000 or less, okay, Reynolds number smaller than 2000. It is in the range of the laminar flow. The points are concentrated on this line. Okay, this is observation 1. This is observation 1. For this region, the frictional factor has a very clear relationship equal to 64 over RED. We talked about previously, okay? We talked about previously. For the laminar flow, the frictional factor has a fixed relationship here, okay? So this is a very clear relationship. Now, you go to the right-hand side of this 2000. After 2000, between the 2000 and 3000, you see that the points are concentrated in this region. It is very unclear distribution. If it is now, if you look into this area, the distribution of the points do not have very clear trend or any clear model. Okay, so that this is unpredictable region. Okay. Unpredictable region between 2000 and 3000. Between the 4,000 or 3,000. Okay, unpredictable region. It is said it's an unpredictable region here, right? So that in this region we will not have any heat model or calculation here. Okay. Now, next is region that is the observation here. The next is the observation here. Now, when it is after 3000, is in a turbulent region. Okay, it's in a turbulent region. in turbulent region, okay, on the right hand side of the 3000. It's turbulent. Now, you see that the points, the dots, are never lower than this line, okay? Never lower than this line. So that this is a smooth wall tube. Because when the roughness, relative roughness, becomes smaller and smaller, it will be more approach to this line, okay? This is 0.001 for the Ks over D, alright? It seems that if the roughness is smaller and more approach to 0, that means the wall of the pipe is very, very smooth. The distribution of the points is close to this line. So that we call this as a smooth wall tube line, okay? Small, smooth wall situation. Ultimately, smooth wall is this line, okay? So that all the dots will not get across lower than this line. This is second observation here. The third observation we may see here, okay? The third observation is this region. This region. Now, the dots distribute in very clear different trend. Okay, you see that the frictional factor in this region is related to the Reynolds number and also the relative roughness in this region. Now, for this white square dots and the solid square dots, okay, the hollow circle dots and the solid circle dots, okay, they have very clear different trend. Okay, so that in this region, it means that the frictional factor is in the relationship of the Reynolds number depends on the Reynolds number and the relative roughness, because this is not linear. Okay, it's not horizontal or linear. Okay, so that it depends on the Reynolds number and the relative roughness. But the fourth region, the right hand side here, okay, the lines even become horizontal. Okay, become very horizontal. So in this region, because it is horizontal, so that the frictional factor is not is no longer related to the Reynolds number. So in this region, that the frictional factor is mainly depends on the relative roughness only. Okay. So that in the region 3 is a transitional flow. It is turbulent flow, but it's not a very rough turbulent flow. And in this region, it's a fully turbulent flow. Okay, fully turbulent flow. So that in the turbulent flow, there are two sections. Okay, one is a transitional turbulent flow. Another right-hand side is a fully turbulent flow. Okay, so that if for your design of the pipe network or design for the pipe, you can have a try. Okay, because most of the time for the water it is the low viscosity liquid, so you can estimate in the fully turbulent flow region. Okay, for finding a relatively rough estimation, okay? Because most of the time, the flow is in the fully turbulent flow region. So that there are 4 observations for this figure, and this figure, it is kinds of the data for forming the Moody diagram. Okay, this figure is from forming the Moody diagram. The nowadays Moody diagram we use is developed from this experimental finding. Okay, that's why I would like to show you that this graph or the raw data. Okay, by analyzing the raw data, you can understand why the Moody diagram look like this. Okay. Now, just now, there is a table that's showing the reference for the relative roughness, the equivalent sand roughness from different pipe material, the KS. Previously, we have also a table to show this value in this figure, in this table, okay? The relative roughness, that is not, the equivalent sand roughness height, okay? So you can also refer to, if the table in this page is not very detailed, you can also refer to the previous table, okay? Now, the equivalent roughness given in millimeter, this is in millimeter, this is in inch, okay? Now, this page shows that the Moody diagram that we will use for calculation using the Darcy-Weisman equation finding the frictional factor here, okay? So that this is the Moody diagram, the same as the previous experimental data. The right-hand side is the relative roughness, Ks over d. The bottom is the Reynolds number. The left-hand side is the frictional factor, okay? Now the laminar flow is the straight line, and the smooth curve, smooth pipe is here, and this dashed line separates that the transitional turbulent flow and the fully turbulent flow, okay? So the upper side, there is an equation to estimate the this group of calculation compared with the RED F1/2, okay? So, but we seldom use this equation, okay? Mainly we use this relative roughness, Reynolds number, and frictional factors relationship more, okay, than this. So this is the Moody diagram. Now, actually, associated with a Moody diagram, you can look for the frictional factor by using the diagram, and we can also have some numerical model to look for it. One of the very popular model is the Suomi and Jain equation. Okay, Suomi and Jain equation to find the frictional factor. This is for the turbulent part. It is for the Reynolds number 4,000 to 10 power 8. Okay. 4,000 to 10 power 8 for turbulent part. For the laminar, okay, you don't need to calculate using this equation. It's 64 over RED, right? For laminar. For laminar flow, you don't need to use this equation because there is already a fixed relationship. Sometimes you may use a Volkamen equation. Okay, Volkamen equation only use the Ks over d so that it may be more applicable to the fully turbulent flow. There is also the Colbert-Wright equation. Colbert-Wright equation. Colbert-Wright equation is also have a very good prediction of the frictional factor. However, for this equation, it is not very convenient like the Suomi and Jain equation because this equation, to find the frictional factor F, you cannot directly find it by just input. You have to use the trial and error to find the frictional factor. Okay, so that it's not the Colbert-Wright equation is not convenient as the Suomi and Jain equation. So this is if you are using the computer to estimate the frictional factor, this will be more preferred. Okay, the Suomi and Jain equation will be more preferred. Now, so this is the Moody diagrams to find for the frictional factor. Actually, associated with the Moody diagram, there are three cases of the problem. Okay, one is to directly look for the head loss, and we will talk about this one in details in the next lecture. Second case question is look for the flow rate. Based on given the information of the head loss, the diameter, the material of the pipe, the length of the pipe, you are going to estimate the flow rate running in the pipe to use this method. This case 2 and case 3 has the iterative approach. Case 3 is look for the pipe diameter, okay? This is more related to the pipe design's purpose. Okay, you are going to find out the necessary diameter by knowing that the head loss information, the discharge requirement, and the pipe material you selected, and the length of the pipe necessary, and you may estimate the necessary diameter and to look for the closest DN pipe. Okay. So there are three problems that three types of the problem that associated with the Moody diagram by using the Darcy-Weisman equation. So at this moment, we will for the lecture content, we may just stop here and go to the tutorial part tonight. For the remaining content, we will given in the more detail in the next lecture. Okay. For tutorial 1, we have uploaded to the Moodle. Now, for the first question, it is about the momentum conservation or momentum equation. Okay. Sorry, the static hydrostatic force. Hydrostatic force. To estimate how much is the force exerted on the plane in this figure, in this setup, okay? Find the location of the resultant force. Find the location of the resultant force, F, on the water on the triangular gate, the force P, and the force P necessary to hold the gates in the position shown in the figure. Neglect the weight of the gate. Okay. Now here is supposed to be a water tank. All right. It's an inclined wall, and then there is a triangular gate here, just like the water is kept. Okay, the water is kept on the left-hand side, right? And there is a triangular gate. This is the hinge. That the gate can be opened like this way. Okay, can be opened like this way to let the water comes out. Okay, the gate can open like this way. All right. So let the water comes out. Now, here we are asked to estimate, okay, how much is the P force to hold this gate in place, and where is the location of the central pressure, okay? Now, to estimate this kind of question for the hydrostatic force on the plane, we mainly have 3 steps, okay, 3 steps. One is the hydrostatic force, the resultant force, or the And the second step, it is find the center of pressure. The third step is to use the moment equilibrium. To find the unknown force, okay? So very first step, the resultant force. Remember that for the resultant force, the pressure force, resultant pressure force, is calculated by the average pressure on the plane and times the area, and equal to the centroid pressure times area, okay? Now go back to the figure here, okay? Now, this is the shape of the triangular gate. For the triangle, here, okay? For the triangle, the centroid is located at the center line, on the center line, okay? On the center line from this vertex to the bottom, the baseline, okay? And on this line, and then the height is 1/3 from the baseline, okay? 1/3 of the height from the baseline. So that the location of the centroid is located the total height of this triangle is 3 meters, okay? So that the centroid is 1/3 from the bottom is 1 meters from here, okay? So that's 1 meter from the baseline. It may be here, okay? It may be here. So this length is 2 meters, and this is C point, okay? And this length is 1 meter, all right? So that we need to look for the HC. We need to look for the HC. Suppose that the water surface is PATM. Okay, the water surface is PATM. And then we may look for the point C pressure by the raw water, the G and HC times the area of the plate, the triangular gate. Okay, HC is not directly given, but we can see that in this triangle. Okay, in this triangle, HC can be determined by the hypotenuse, by this edge, 5 meters times 5 meters plus 2 meters times the sine 53. Okay. So the HC can be determined by the rho G. It is 2 plus 5 meters times the sine 53 degree. Okay, HC can be calculated by this way. And the area. Now, the density of water can be estimated by the water density can be, we assume that it is 1,000 kg per meter cube. Gravity is 9.81, or we may directly use the rho G, the gamma. The specific weight is 9810 to save time, which is 1,000 times 9.81, okay? Times 7, all right? 7 times sine 53 degree times the area of this triangle. So it's supposed to be the bottom width is 2 meter and the height is 3 meter. It is a right triangle here, okay? So it's like the 1/2 times 2 meter times 3 meter, okay? For the area, for the resultant force. The resultant force is calculated to be, it's not given in bottom answer, we can do it by ourselves. So it's 9810 times 7 times 3 times 53 degrees sine. It's about 164.5 kilonewton. It's around 164.5 kN, okay, kilonewton for this resultant force. Next is the location of the center of pressure, okay, center of pressure. Now, the center of pressure we can see from this figure, okay, or here. The center of pressure, CP, is this point. As we said, the center of pressure is the action point of the resultant force, or the pressure force, which is supposed to be lower than the, a little bit lower than the centroid. And we estimate the distance from the center of pressure to the water surface. Now, from the centroid to the water surface, this is YC. And from the center of pressure to the water surface, this is, maybe I use different color to make you see it clearer. Use purple. Okay. This is YP. Alright? Purple to the COP, to the CP is YP, okay, or YCP. Now, this is the center of pressure. The location of center calculated from this location. Now, the YC is 5 meter plus 2 meter, okay? YC is 5 meter plus 2 meter. The center of pressure. Now, firstly, we see that the YC is 2 plus 5 meter. Is 7 meter, okay? The YP supposed to be the center of pressure equation, YC plus IXXC over YC times A. Now YC is have been determined. Area is calculated as 3 square meter. IXXC, it is the calculation based on this. AB cubed over 36. AB cubed over 36. A is the bottom width of the triangle. B is the total height, okay? Or we can try to use it to simplify the calculation. Is AB cubed over 36. YC times the area of the triangle is A times B over 2, alright? Canceling this, become 2. And this becomes 18, okay, power 2. So it's B power 2 over 18. So that we can calculate the YP is like 7 meter plus is B squared. B is totally 3 meter over 18 times 7, okay, YC 7, or 7 times 18, okay. So the result is determined to be 7.071 meter from the surface, okay. Number 3, to find the force P necessary. For example, it may be a stopper, okay? You may have a stopper to control the opening and close of the gate, so that you may need to estimate how much is the force necessary to open it or close it, okay? Alright? Now, moment equilibrium, we can see from this figure. So, the solid line indicates that the gate's location, okay? This distance is 5 meter, and the YP is 7.071 meter. So that this length for this location, okay? This part is 2.071 meter. So because we need to estimate the moment for the F times the to the hinge point here, okay? To the hinge point here. So that this distance is we can say it's 3 meters subtract 2.071 meter. Alright. So for the moment equilibrium, the F is making the rotation of the gate is to be the clockwise, okay? The P is making it rotating counterclockwise. So the relationship is the F out, the resultant force times the 3 subtract 2.071 is equal to the P force times the moment up, which is 3 meter. So the P is therefore calculated as like the F out, which is 164.5 kilonewton. We can times the 3 subtract 2.071 and over the 3 meter, and this one is found to be about 50.9 kilonewton. Okay, it's about 50.9 kilonewton. All right. So this is the location, the force P necessary to hold it in place. However, it's not all finished, because the question is also asking us to find the location. Now, because the center of pressure is not is on the center line, okay? So we need to locate we have located a vertical location, which is 2.71, all right, from the vertex. However, the horizontal location is unknown, okay? Now, we can magnify this triangle, okay? We can magnify this triangle. This is the right triangle. the CP is on the center line, okay? Supposedly this is the centroid. We may use the similar triangle, okay? Or maybe we can directly use this one, okay? If this point is CP, we can use similar triangles method. The total, from here to here is 2.071 meter. From here to here, the total height is 3 meter, right? Now, you can estimate how much is the distance here, okay? The distance from the bottom line, the bottom edge is half width is 1 meter, okay? 1 meter, because the total width is 2 meter, half width is 1 meter. So that is to find out the horizontal coordinates for the center of pressure. The vertical location is 2.071 from the on the center line for this top vertex point. Okay, for the similar triangle. Now, the 2.071 over 3 meter is equal to the x location over 1 meter. Okay, so the x is found to be about 0.690 meter from any one of the side, okay, any one of the point, because sorry, this one. This one, okay, is 0.690. The y location is 2.071 from the vertex, alright? So to locate the x is 0.690 from one of the edge, okay? So this is the solution for the problem 1. For the question 2, there may be very long solution steps. So I will talk about the question 3 first. Then we will talk about the question 2 later, next time, okay? Question 3, a glass tube is inserted into a flowing stream of water with one opening direct upstream and the other vertical. If the water flow velocity is 5 meters per second, seems that there is conflict, okay? Here is 5. Here is 5. Figure shows 4. Okay, we use 5 meters for calculation. How high will the water rise in the vertical length relative to the level of the surface of the stream? Okay, so it is asking how much is the the water level difference. Actually, we have analyzed this situation in the lecture, okay? Now, here is location 2. We say the location 2 here. Any one of the point dots before it, we say it's location 1, okay? In this figure, we may use the Bernoulli equation. Bernoulli equation. Bernoulli equation. full Bernoulli equation is the P1 over gamma plus Z1 plus V1 square over 2G is equal to the P2 over gamma plus Z2 plus V2 square over 2G. Right? Now, we can analyze now. The Z1, Z2 are cancelled due to the same location, same elevation. Okay, same elevation. They are cancelled due to the same elevation. Alright? V2 is static, okay? Stagnation point. Cancel, okay? Is 0. This is due to the V2 is a stagnation point. V2 is static because it is in the front or on the intersurface between the flowing fluid and the tube, the stationary fluid. So that the V2 is 0 velocity here, okay? So this equation can be simplified to be the P1 over gamma plus V1 square over 2G equal to P2 over gamma, alright? Now, we see that the P1 over gamma, if we say this pressure at point 1, it is contributed by the water pressure, steady pressure. Okay, so the P1 over gamma. P1 is rho G A1, A rho G A over gamma, right? Plus V1 square over 2G is equal to P2. P2 is contributed, the pressure is contributed by the liquid in the tube. It's not just the rho GA, okay? It's a rho G, the height is from this top level, okay? Is L plus A, alright, over gamma. Now gamma cancels that the rho G. So the remaining is, alright, the remaining is A plus, is V1 square over 2G is equal to L plus A. A and A are cancelled. So the V1 is, the L is equal to V1 square over 2G. L is equal to 5 meters square over 2G, 2 times 9.81. And the result is found to be 1.27 meter. Okay, 1.27 meter. This is a straightforward question to analyze the using the Bernoulli equation. Okay. Now, so this is also indicates that for the velocity measurement, okay, we can use that the L times the square root 2GL, okay, in this situation to measure the velocity height. V1 is equal to square root 2GL, in other words, okay? So that's why we can use the pilot tube to measure the velocity of the flow in here, okay? So, and also, now additionally, if there is a zero configuration, now you can see that in this point. For the location 2, you can see here. For the location 2, or for the location 1, maybe location 1. This is Z1, okay? And this is A is equal to the P1 over gamma, right? Now, the V squared over 2G is equal to the L. So that the V squared over 2G, V1 squared over 2G is the height of the L, the same, right? So that we see that the water level in here, it represents that the distance here actually represents that the P1 over gamma plus Z1 plus the V1 squared over 2G, which is the HGL. Sorry, EGL, the AGL's level, okay? And the water level here, and the visible flow water level, okay? It is calculating the P1 over gamma plus elevation 1, okay? So that the visible water level, it represents that the HGL, the hydraulic grade lines level. And if you use the pilot tube to measure it, okay, the level, the absolute level for the water in the tube indicates that the EGL's level, energy grade lines level, and it represents the total energy. Total head, okay? And this HGL represents the piezometric head. Or we can say this piezometric head represents the potential energy, okay? Represents the potential energy. So, so that that's why when you are plotting the sometimes that you see in this figure. That's why in this figure, okay, for the energy grade line, in here, okay, in this figure. So that's why if there is a stagnation tube or the pilot tube inserted into the pipe, that the water level will be higher than the simple manometer. Simple manometer represents that the pressure head, okay, the pressure head, and together with the elevation, it means that the piezometric head for its visible water level. And if for the stagnation tube or the pilot tube, the visible visible water level indicates that the height of the EGL, because it adds the additional velocity S level. Okay. Now I think that the time is just come to here for the tutorial session. So here is this is all of the content that will be delivered for the lecture tonight and the tutorial tonight. Okay.